Look at this generated video. It begins with a pristine T2-weighted MRI scan of a human brain, but quickly degrades into an unreadable image, fractured by ghosting, chemical shift, and herringbone patterns. To an untrained eye, this looks like random digital noise, but there is no true randomness here. MRI artifacts are predictable, mathematical signatures. They are exact readouts of a physical disruption occurring somewhere in the imaging pipeline. The Fourier transform operates on three physical assumptions: a homogeneous primary magnetic field, linear spatial gradients, and a stationary target. When any of those conditions fail, the math breaks. By mapping these failures chronologically, starting at the local magnetic field, moving through the spatial encoding gradients, and finally into the digital compilation of K-space, we can see exactly how physics distorts the final data. For the advanced radiologist, assessing the patient requires first diagnosing the mathematical breakdown of the machine itself. Distortion begins with deviations in the local magnetic field. The primary field, or B0, is meant to be uniform, but the presence of metal implants, air-fluid interfaces, or even boundaries between different tissue types disrupts this homogeneity. The human body is mostly fat and water. Even within the same uniform 1.5 Tesla magnetic field, the protons in fat and water resonate at slightly different Larmor frequencies. This diagram illustrates what happens during frequency encoding. The scanner uses precessional frequency to map physical location. Because the fat vector is rotating at a slightly different speed than the water vector, the scanner misinterprets the fat signal. It plots it into an incorrect position along the frequency encoding axis, a phenomenon known as chemical shift. That positional error occurs at macroscopic boundaries. But when microscopic fat and water protons exist within the exact same voxel, their differing frequencies cause their waveforms to continuously drift in and out of phase over time. At precisely 2.24 milliseconds in a 1.5 Tesla field, these two waveforms reach total destructive interference. The signals cancel each other out completely. Clinically, this fat-water cancellation projects a distinct black boundary line between tissues on the image, nulling the signal entirely. This shifting frequency also compromises specific imaging protocols. Fat saturation techniques rely on a narrow radiofrequency pulse targeted exactly at the fat peak to null its signal. Rapidly changing anatomical contours, like the shape of an ankle, warp the local magnetic field just enough to shift the fat frequency outside that targeted RF pulse, causing the saturation to fail. Anytime the local field loses its homogeneity, it forces the scanner to plot technically accurate Larmor frequencies into false physical realities. Moving beyond the local field, we hit the gradient spatial encoding phase. The timeline of data acquisition here exposes the scanner's greatest structural vulnerability. Look at how this field of view grid is filled. Frequency encoding, the rapid horizontal sweep, happens in milliseconds, fast enough to effectively freeze motion. But phase encoding, the vertical step down, requires multiple repetition times to complete. Introduce cardiac motion or respiration into this equation, and the timing disparity becomes obvious. The anatomy shifts position between the slow vertical phase steps, permanently corrupting the alignment of the collected data. Because the error happens entirely within the slow vertical sequence, the resulting artifact is highly directional. The SCADA projects asynchronous, low-intensity copies of the moving anatomy strictly along the phase encoding axis, creating the visual stutter known as ghosting. This axis is equally vulnerable to spatial boundary errors. Phase wrap, or aliasing, occurs when the patient's anatomy extends beyond the prescribed field of view during phase encoding. The scanner undersamples the signal coming from outside the boundary. Mathematically unable to process this isolated data, it folds or wraps the anatomy back onto the opposite side of the image. The solution requires strictly adjusting the phase encoding parameters, either by expanding the field of view or oversampling the data. The phase encoding direction acts as the primary temporal bottleneck for the entire scan, trapping both patient motion and spatial limits in its slow acquisition. Once spatial encoding is complete, the focus shifts away from scanner hardware and into the digital compilation of K-space data. This K-space matrix represents the raw spatial frequencies. External variables like static electricity buildup on clothing or faulty equipment leaking spurious RF signals inside the room can inject a surge of noise into the collection process. This registers as a bright anomalous spike in a specific data point. When the Fourier transform processes that single rogue wave, the error does not stay confined to one pixel. It expands outward, translating the localized K-space spike into a global herringbone pattern of alternating dark and light bands across the entire final image. A similar digital translation error occurs at the very edges of anatomy, creating the Gibbs artifact. To render a sharp boundary between two tissues, the Fourier transform requires high-frequency data points. However, K-space is finite. Truncating the data acquisition before enough high-frequency points are collected makes it impossible for the math to accurately model steep contrast drops. Instead of a clean edge, the truncated data produces a series of superimposed oscillating waves. In spinal imaging, this artificial ringing mimics the appearance of distinct physical lesions right at the boundary between the spinal cord and the cerebrospinal fluid. In the digital realm of K-space, localized errors do not exist. A single corrupted data point or a missing high-frequency variable guarantees a distortion across the entire image. Pushing an MRI for maximum diagnostic speed requires specialized protocols, but extreme speed inherently amplifies these underlying physical vulnerabilities. Echoplanar imaging, or EPI, is one of the fastest sequences available, acquiring all of K-space in a single radiofrequency excitation. To achieve this, the gradient rapidly traverses K-space back and forth, but this continuous reversal causes minute misalignments in the data echoes. The resulting distortion projects distinct N/2 ghosts, low-intensity copies shifted exactly half the field of view away from the true anatomy. Fast spin echo sequences take a different approach, acquiring multiple lines of K-space per excitation. The number of lines acquired is the echo train length. A very long echo train length saves time, but it allows T2 relaxation to occur continuously while the data is still being gathered. The fading signal introduces progressive blurring along the phase encoding direction of the final scan. Steady-state free precession imaging maintains a rapid, continuous signal, but it is acutely sensitive to the local magnetic field. Even minor inhomogeneities cause the stimulated echoless to constructively and destructively interfere, resulting in a distinct dark banding pattern across the image. Every attempt to bypass the temporal limits of the scanner exposes the baseline fragility of the magnetic field and the math interpreting it. Understanding these mechanisms provides a clear diagnostic framework. The physical source of an artifact can be reverse engineered by examining its mathematical geometry on the scan. Look at this matrix. Rule 1. If the visual error is strictly directional, the failure occurred in the gradient timing. Temporal delays along the slow phase axis result in ghosting or phase wrap. Rule 2. If the error is global and geometric, the failure occurred during data collection. Spikes or truncations in K-space translate into systemic Fourier distortions, like the herringbone or Gibbs artifacts. Rule 3. If the error involves signal voids or positional shifts at tissue boundaries, the local magnetic field has broken down. These inhomogeneities trigger Larmor frequency shifts, causing chemical shift and fat-water cancellation. Mastery of MRI physics means recognizing the precise moment mathematical models collide with physical reality.